When we've been dealing before with the work-energy theorem, which looks like this, work equals change in kinetic energy, this is the total work, net work, okay? And I think you've probably seen that when we've got a whole bunch of forces on an object, or even if we just have one force on an object, having to list all those works and add them up becomes a little grueling, okay? One thing you can do is you could find the net force on an object, find the work done by the net force. So F times the displacement times the cosine of the angle in between the net force and the displacement. And you could do it that way. But there's a way of using this that we do it a little differently, okay? And that's called potential energy. Because in almost every equation, in almost every problem, you're going to have gravity doing some work, okay? And gravity does an amount of work. If we think of the work done by gravity, it's going to be the force of gravity, mg, times the displacement, times the cosine of the angle in between those two things. Well, the force of gravity is always down, okay? And if you think of, let's just say going down the ramp, let's say that's the displacement. The angle in between those things, this theta, really is just like saying, let's figure out how far down the object goes, how far down towards the center of the earth the object goes, which is delta x cosine theta. Well, there's an easier way of looking at that. Instead of thinking of all this cosine theta and all that, if we just say, how far does the object move down? Height, change in height, and the force. Then the work done by gravity is just force times the change in height. mg times the change in height. So since we use this so often, we talk about a thing, we replace the work done by gravity by this thing called potential energy. Okay? And potential energy is nothing harder, nothing more complicated, and we write it as U is the potential energy. Okay? And the gravitational potential energy is just the mass times g times the height above some reference point, okay? And when I say some reference point, I'm not trying to be mysterious. Let's think about this. Let's think about, we got a table, and I'm holding a ball right up here, and I'm going to drop it onto the table, okay? Well, it makes sense to say that's my reference height. I'm going to call that height 0. And so the height above that would be however high I'm holding this thing. Okay, let's say it's 2 kilograms, and let's say I'm holding it 0.2 meters above the table. It's almost meaningless to talk about the potential energy relative to the ground. But here we're saying, oh, okay, if I dropped it, I would in a way be converting all that potential energy into kinetic energy. So this potential energy is how much energy we can convert into some other form. Okay, so in this case, the potential energy would be mass 2 times g, about 10 times 0.2. 20 times 0.2 is 4 joules. Okay, and that's saying it's 4 joules relative to the table height. So we're always talking about relative. Potential energy is always relative. It's not a real energy, right? Because think of this. Suppose I stacked a whole bunch of books up, and that ball's sitting on there. 4 joules of energy, well, it's just sitting there. What does that mean? It doesn't really mean anything. If I were talking about relative to the floor, that height would be higher, right? So if I were going to drop this thing onto the floor, does it magically have more energy just because I'm measuring from a different place? So potential energy is kind of a fake energy. It's a placeholder. Potential energy replaces work done by gravity. Okay, we do it because we use it so often. Gravity is so often used in this that we don't want to have to do this mg cosine theta times the delta x every time. So it's a way of simplifying some problems. Okay, so let's take a look at that really quickly. First of all, let's just talk about measuring that potential energy. If we talk about, as I say, relative to a certain spot, relative to a certain reference height or reference point, then we can talk about, let's talk about the book on a table. Okay? Book on a table, I'm not even going to bother erasing all that. A book on a table. Okay, so here's the table, and the table is 1 meter high. Okay, there's the floor. And we've got a book on the table. Okay, and let's say the room is 3 meters high. So remember that the potential energy is just mass times g times the height above a reference height, a reference point, reference. Okay, so we have to kind of define, what are we calling zero? What are we calling zero height? Where are we calling zero energy? So if I said relative to the floor, and let's make this a 2 kilogram book. So relative to the floor, in other words, if I call my floor zero height, then this potential energy would be 2 times 10 times 1 meter is 20 joules. Okay. Relative to the table, 2 times 10 times 0 joules. Times 0 meters, which is 0 joules. Relative to the ceiling, if I called the ceiling zero height, this has a height of -2. So compared to the ceiling, 2 times 10 times -2, which is -40 joules. All of these are meaningful. Okay, all of these are meaningful. If I lost my microphone there. If I'm thinking this book might slide off the table and crash to the floor, I might be interested in in this measurement. If I'm thinking I might throw that book up in the air or something, I might be interested in this measurement. You can really pick anything to be your reference point if you're using MGH. You can pick anything to be your reference point as long as you're consistent. Height is always, up is always positive though for height. But you can pick anything to solve your problem as long as you're consistent. Okay, so I'm going to now talk about dropping that book, and okay, I'm going to talk about, that book slides off the floor, off the table onto the floor, and I'm going to show you how we use potential energy. And I want to find out how fast that book is going when it reaches the floor. And of course we can do this with our normal Newton's second law and our kinematics equations, but I want to show you how we solve that with energy. Okay, so the ball is going to fall off the table and go to the floor. And I'm going to do it a few different ways. So first, let me do it relative to the floor. So floor is 0. Okay, floor is 0 height. As I said, the potential energy here is going to be m times 10 times 1, so 20 joules. Okay? When it falls down, the potential energy when it gets down there is going to be 0 joules, right? It's at 0 height. So what we say is lost 20 joules of potential energy, so it must have gained 20 joules of kinetic energy. So the change in kinetic energy is positive 20. And this is part of a thing that I'm going to introduce in much more detail in the next video that's called conservation. of energy. And so basically what's happening here, and this is the way I want you to remember it, potential energy plus kinetic energy at one time, I'll just call it 0, is going to be equal to the potential energy plus the kinetic energy at another time, unless there's some work done by some other form, okay? So if there was friction or something like that. So work from external source plus the potential energy plus the kinetic. And notice now I don't have to worry about potential energy, gravity, as being an external source of work. It would only be applied forces and friction and things like that, okay? So this is really conservation of energy right here. Total before equals total after, unless you're adding something to the system. And I'll cover that in great detail in the future. But if we don't have any external work done on this, it's just the book falling down, then we have at the beginning we had 20 joules and no kinetic energy. It's from rest. And afterwards we had 0 potential, so the kinetic energy has to equal 20 joules. At the end it had 20 joules, and since it started from rest, the final kinetic energy is 20 joules. I'm going to put a box around that. I'll show you why. Because kinetic energy is actual energy. It's energy because it has mass and it has a velocity. But what I want to do now is I want to switch. I showed you that is if I call the ground 0 height. Okay? Now though, what I want to do is I say, what if we called the desk 0 height? Okay? If we call the desk 0 height, we're going to get some slightly different situations here. Okay? So if the desk is now 0 height, right? Well, mg times 0 is 0. It starts with 0 joules of potential energy. And again, I told you it's a fake energy. It's relative to a certain position. Two people could pick different positions and still solve and get the same result. When it goes down, it's now got a potential energy of 2 times 10 times -1. It's 1 meter below the 0 reference. Times -1, that's -20 joules. So at the beginning it had 0, and it had 0, it was at rest, kinetic energy. At the end it has -20 plus whatever the final kinetic energy is. Well, you solve it, guess what? Kinetic energy is 20 joules. So really it doesn't matter what you pick to be 0 as long as you're consistent. In other words, you can't pick 0 at the beginning to be the desk and then 0 at the end to be the, you can't, no, it's got to be one solid reference point. Now I'm going to show you, take it one step farther, and I'm going to say, I'm going to call the ceiling 0. What? That doesn't make any sense. Well, it kind of does, and when we get to gravitation, you're going to see why I'm setting this up this way. So if now I call this 0, well, the potential energy of the book at the very beginning is 2 times 10 times -2 is -40 joules. At the end, it's 2 times 10 times -3. It's 3 meters below where our reference point is. So that's -60 joules. And I think you can see that the change in potential energy, it went from -40 to -60. -40 plus 0 equals -60 plus k. Any way we solved that, we found 20 joules for the kinetic energy at the end. So we know exactly how fast it's going if we use 1/2 mv squared. 1/2 times 2. So this is going to be v squared. Square root of 20 would be the velocity any way I solved it. So this is how we use potential energy. I should say specifically gravitational potential energy. We use gravitational potential energy as a placeholder to replace the work done by gravity. Just because we do the work done by gravity so often, it's a way of making it a little simpler. And that equation, gravitational potential energy equals UG equals mgh. Very, very simple. G is 10. You've got the mass. You just plug in the height and you've got the potential energy. Makes it a whole lot easier than doing all those work calculations that we had to do before. So, big point. That is our new equation, potential energy, gravitational potential energy. The work energy theorem, work total equals delta K. This is still true if you represent all the works individually and add them together. You'll still get that change in kinetic energy. But this is much more useful if we want to talk about a conservation of energy concept where we're not representing all the works there. We are using this instead of doing the work energy theorem. So I'll show you problems later that kind of reinforce the fact that it's sort of this or this. This is always true, but this is true if we want to use this as a placeholder to simplify the math a little bit, and we use this in conservation problems, which we're going to see next.